Hey everybody, we be doing our next section. Here's the good news. All right, we only have five more sections to cover: 5.3, 5.4, 5.5, 5.6, 5.7. All right, and only two more assessments. All right, today, 5.3 and 5.4 go together. That's all the notes that are right here. All right, we're going to split this up into 2 days, and then you're going to be taking a partner quiz. Although I think some of you already, every quiz is a partner quiz for you guys. Um, you'll be taking that, and then we'll do the last three sections, and you'll take one last assessment, and that will take us right into the beginning of June-ish, and then we will be stopping there. Okay. Um, so what we're going to be talking about first is probably should be a little review, and is of inverse functions. Okay. Um, if you see this notation right here, f to negative first, that means the inverse of f. Okay. Two ways you can show that they're inverses. First, algebraically, if you were to take two functions, and if you do f of g of x, then if you do the other composition, g of f of x, if they both equal x, then you have an inverse. Graphically, you can tell because they are a reflection over the line y equals x. Y equals x is this dotted line right here. Okay, so you can see the red and the blue lines here. If you were to flip them over that line, you would get the same thing. Okay, so the domain of f is the range of g. The range of f is the domain of g. All right, basically what you do, if you remember, you're just flipping the x's and the y's. And if you get the same thing, then it's an inverse. Okay, every function does not have an inverse. Okay, the way to tell whether a function has an inverse or not has to pass the vertical line test and the horizontal line test. Okay. And then must be, so you guys have seen that before. What you might probably not have seen before is this: must be monotonic, which means the function is either always increasing, right? So something has to be always like going up, or always has to be decreasing. It can't be like this, because this isn't always increasing and decreasing. It's increasing there, then decreasing, then increasing. This would not have an inverse. All right. Also, because it doesn't pass the horizontal line test. Now, how can we check to see if something is always increasing or decreasing? Well, if you remember way back when we test that, that was a first derivative. All right. And I can't spell derivative. You guys get the, I don't know why it's not showing up. Derivative. Okay. All right. So, for example, if you look at y equals x to the fifth plus x cubed plus 3x minus 7. And let me just blow this up. We're going to lose all of this, but who cares? Okay. All right. So if I take the derivative of this, okay, if I take x to the, it would be 5x to the fourth plus 3x squared plus 3. Okay. Now, for any positive x value I throw in there, what would happen? That'd be positive, positive, everything's positive, which means it'd be increasing. All right, because remember, if you plug a number, if it's the first derivative is positive, that means the original is increasing. If you plug a number into the first derivative and it's negative, then it's decreasing. All right, if I plugged in 0, I get 3, which is positive, so that's increasing. Any negative number, what would happen if I threw a negative number in here for x? If I raise to the fourth, it becomes positive. A negative number in here, squared, I know you can't tell, but that says squared, also be positive. So for all x's, no matter what I put in there, for all x's, it is, you would get a positive, which means it is always increasing, which means it is monotonic, which means it could have a inverse. Okay, it's always increasing. All right. Now, how do we actually find the inverse? All right, to actually find the inverse, and you guys did this back in pre-cal and some of you in algebra 2, all right, is to substitute y's for x's, all right, and x's for y's, and then you're going to solve for y. So remember, f of x just really means y equals the square root of 2x minus 3. All right, so what I'm going to do is I'm going to make it x equals the square root of 2y minus 3. All right, I am then going to solve for y. So I got to get rid of the square root, which means I'm going to square both sides. All right, so I get x squared equals 2y minus 3. I then add 3 to both sides. 2x plus 3 equals 2y. And then finally divide by 2. So the inverse, whoops, that's a crazy looking f, but actually doesn't look that bad. The inverse of f of x is then equal to x squared plus 3 over 2. All right. That's how you find the inverse. All right. All right. Let's try one more. All right. So remember, that's y equals same thing. So I'm going to substitute it. All right. So I get x equals 2y plus 1 over 3y. Now the issue is here we have 2y. So what's going to end up happening? We are going to get rid of that denominator. We don't like it. So let's multiply both sides by 3y. So I get 3xy equals 2y plus 1. All right, now, whenever you have two terms like this with y in it and we want to solve for y, we want to get all the y's on one side. So 3xy minus 2y equals 1. But I can't combine them. So what you have to do is you take out a y. So it's 3x minus 2 equals 1. And then divide by 3x minus 2. So y equals 3, whoops. Sorry about that. 3y is equal to 1 over 3x minus 2. And that is your inverse. All right. That is your inverse. All right? So you substitute the x and the y's, and then you solve for y. All right. So I think you guys hopefully have seen that before, but that's how you find an inverse. All right. Now, to prove something algebraically, all right, so check your answer for example 2 using the algebraic proof. Okay. So to do that, all right, this is what we'll call our like f of x. This will be like our g of x. And we have to do a composition of functions, which means I have to put all of this in for that x. That's the first thing I'm going to do. So if I get the square root of 2 times x squared plus 3 over 2 minus 3. All right. I just took all of this and plugged in for that x. Now what happens here is that those cancel. And I'm left with the square root of x squared plus 3 minus 3. These 3's cancel. I'm left with the square root of x squared, which is just x. And that's what we want. All right. Now we have to do the opposite now. We have to take all of this and plug it in for that x. All right. So we have to take the quantity of the square root of 2x minus 3, all of that squared, plus 3 all over 2. All right, so we're doing f of g of x and then g of f of x. Well, when you square a square root, you get rid of the radical. So it's just 2x minus 3 plus 3 over 2. Negative 3 plus 3 cancels out. The 2's cancel out, and you're left with x. So since I have x there and x there, I have now proved algebraically that these two functions are inverses of each other. All right, so that's, if it ever says algebraically to prove how two functions are inverses of each other algebraically, that's what you do. All right. So that's that. Now, why are we talking about inverses? Well, last section we talked about natural logs. Well, guess what? Does natural log of x have an inverse? It does. All right. The inverse of a natural log is actually an exponential. All right. It is y equals e to the x. All right. I'm not going to go through and algebraically go ahead and prove that, but you very easily could. I mean, you're just substituting in this in for that x, and then you're substituting that into there. So for example, let's just do e to the x instead of e to the x, it's e to the natural log of x. Well, we've learned that on the last quiz, right? If you base a log in an exponent, it's the same base. E is the base of this, e, so this is equal to x. And then, I guess I'm not supposed to do it, the natural log of e to the x, I could bring the exponent out front, which is x, natural log of e. The natural log of e is just 1, which leaves you with just x. So you get x and x, all right? So y equals e to the x. If you look at the graphs, here's our log basic graph. Here is our exponential. Y equals e to the x. All right. So we are going to be doing stuff with exponentials right now. All right. And it's going to be e to the x. Now, just like we did with logs, quick little graphing review. There's the basic shape. It has a horizontal asymptote at 0. And the point we're dealing with now, instead of 1, 0, since the inverse, we're dealing with 0, 1. All right. So just a quick little review here. So here is going to move it to the left 1, right? It's going to move it to the left 1 because I set this equal to 0. The horizontal asymptote does not change, but instead of being at 0, 1, move it to the left. It's going to be at negative 1, 1, and there is my graph. All right, that point, negative 1, 1. All right, this moves it up 1, which since it's a horizontal asymptote, the horizontal asymptote instead of being at 0 is now at 1. Instead of being at 0, 1, I'm now at 0, 2. And just draw your graph. All right, 0, 2. All right, so this negative up front is a vertical flip, which means we're still at 0, but instead of being at 0, 1, we get vertical flip to 0, negative 1 because it changes the sign of y. This negative is a horizontal flip, which means, well, the point stays exactly where it is, but instead of going up like this, it now goes like that. All right, so just like we do with natural log, just real basic graphs of that. All right. Now, solving equations, exponential equations. So if you have an exponential, so to solve exponentials, we're going to use logs. To solve logs, which we're going to do next, we use exponentials. Okay, so we are going to isolate the exponential. It's isolated, all right? Then we're going to take the natural log of both sides. All right, now what you have to remember, so natural log of 7 equals, what happens with exponents with logs? You can move it to the front. So x plus 1, natural log of e. The natural log of v, you have to remember, is equal to 1. So that's gone. That's just equal to 1. So we have natural log of 7 equals x plus 1. To solve for x, we just subtract 1. So natural log of 7 minus 1 is equal to x. There's your answer. Natural log of 7 minus 1. All right. So why don't you go ahead and see if you can get number 2. All right, so what should have happened, we need to get this by itself first. So we subtract 8. So you get e to the 2x minus 4 equals 2. I then am going to take the natural log of both sides. So isolate first. So when I take the natural log, this exponent moves up front. So the quantity 2x minus 4 of the natural log of e equals the natural log of 2. This is now 1. We then are going to add 4 and then divide by 2. So x equals the natural log of 2 plus 4. All of that over 2. And just leave it like that. There's your answer. All right, hopefully you guys got that. So that's how to solve an exponential. To solve a logarithmic, now instead of isolating the natural log, the exponential, we're now going to isolate the log. And then we're going to exponentiate. We're going to raise each power with the side with base e. All right. So this is like left, right, left. We're going to figure remember, if this is base e, get that out of there. It's this to that power has to equal that. So it's e to the 5th. So left, right, left. E to the 5th equals 2x minus 3. We now solve for x, which is e to the 5th plus 3 equals 2x, and then divide by 2. So you get an answer of e to the 5th plus 3 over 2. All right. Now, if you want to, you have to isolate logs first, right? So let's get it so that the logs are all on one side. And let's make it so they are on the left, okay? So I have the natural log of 3 minus the natural log of 4x plus 3 equals -2. Now, if you have more than one natural log, before you exponentiate, let's condense this. So this is the natural log of 3 over 4x plus 3 equals -2. All right. Then we exponentiate. It's e to the -2 equals 3 over 4x plus 3. All right. Then, you know what? To make it easier, because we're going to get a bunch of negatives, and then we're going to have to multiply here and divide. Should have kept this on the right side. You're going to get the right answer, but I'm going to make this a little bit easier for us. Let's make it 2 equals the natural log of 4x. Then we made negative exponents. I was just being silly. The natural log of 3. You've actually got the right thing. You're going to have to do some more algebra, which I don't feel like doing, and I'm sure you don't either. All right, so 2 equals the natural log of 4x plus 3 over 3. All right, because it's a minus. That's why it's on the bottom. So now I exponentiate, and this is an e, so it's e. So now we have to go this way. That's the only reason I was going to do it the other way, because left, right, left, but whatever. 4x plus 3 over 3. Get rid of the 3 by multiplying by 3 on both sides. So it's 3e squared equals 4x plus 3. We subtract 3 and then divide by 4. And there's our answer, 3e squared minus 3 over 4. All right, which you would have got that even if you did it this way. All right, you would have had to multiply by here, and you would have been able to do it, but it's much easier to do it this way. So I apologize. Stupid Mr. Filler. Okay. So that's where we're going to stop for now. All right. It's a good place to stop. What we will do next time is you'll see we'll do the derivative and the integrals. And it's just same stuff we've been doing. There's formulas. You're going to follow the formula sheet. We now will have a new way to use substitution. And we'll end up with e to the u du, and we'll figure out what that's equal to. So that will be our next class. All right. One more lesson down, a few more to go. All right. Hope all is well. Talk to you later.